Hello everyone, my name is Yiming Zhao. The paper I'm gonna present is reverse shortest path problem in weighted unit graphs. This is a joint work with my supervisor, Dr. Haitao Wang. Okay, let's start. Given a set P of n points and a parameter r which is larger than 0, a unit graph is an intersection graph of congruous disks centered at the points of P with a radius of r/2, which means an edge connects 2 points if the distance between these 2 points is at most r. We have 2 ways to assign weights to each edge. So in the unweighted case, each edge has a weight of 1. In the weighted case, the distance between these two endpoints is used as the weight of this edge. And the distance between 2 points is the length of a shortest path connecting these 2 points in the unit disk graph. And we can also define L1 unit disk graphs if the distance between 2 points is measured by the L1 metric. Next, we consider the reverse shortest path problem. We are given a parameter lambda, which is larger than 0 and 2 points s and t in P. And we need to compute the smallest parameter r, which is denoted as r star, such that the distance between s and t in unit disk graph with respect to parameter r star is at most lambda. Note that the distance between two fixed points s and t over the parameter r is monotonically decreasing. And there are some single source shortest path algorithms for unit disk graphs. For our two-weighted case, we have an algorithm which takes n log square n time. And for the unweighted unit disk graphs, we have n log n time algorithm for both L1 and L2 weighted case. If all the input points are pre-sorted by their x and y coordinates, then we can have a linear time algorithm. For the L1 weighted case, we have an algorithm of n log n time. And Cabello and Jesse have proved that the lower bound for the single source shortest path algorithm is n log n. And we also have some RSP algorithms for unit disk graphs. All of these algorithms based on an observation that r star must equal the distance of 2 points of P in all cases. Cabello and Jesse gave a straightforward solution which takes n to the 4 over 3 times log cubic n time in 2015 for L2 unweighted case. Wang and Zhao later gave 2 algorithms which take lambda times n log n time and another algorithm of n to the 5 over 4 times log to the 7 over 4 n time. The first one is good when lambda is small. Very recently, Kaz and Sharia gave a randomized algorithm whose expected running time is n to the 6 over 5 plus epsilon for both unweighted and weighted cases in L2 unit disk graphs. And in this paper, we give an L2 weighted algorithm which takes n to the 5 over 4 times log 5 over 2 n time. And we also solve the RSP problems in R1 unit disk graphs for both unweighted and weighted cases in n log cubic n time. And we also have a byproduct which is an L1 distance selection algorithm. This algorithm will report the case smallest L1 interpoint distance among n points. And the running time of this byproduct is n log cubic n time. Due to the time limit, I'll mainly focus on the L2 weighted algorithm. And our results have been presented in another workshop. We first give an overview of our algorithm. So the basic framework is to first define a decision problem, which is given a parameter r. We need to decide whether r is larger than or equal to r star. We have an observation that r is larger than or equal to r star if and only if the distance between s and t in unit disk graph with respect to parameter r is less than or equal to lambda. So we can use a single source shortest path algorithm as a decision algorithm. In this paper, we use the algorithm of Wang and Xue, which is proposed in 2020. We refer to this algorithm as WX algorithm. The running time of WX algorithm is n log square n time. It's n log square n. The basic idea is to maintain an interval R1, R2. The left side is open and the right side is closed. And we ensure R star is in this interval. And we do a parametric search to shrink the interval. In this parametric search, we will parameterize the WX algorithm. So we first review the WX algorithm. In this algorithm, we will maintain an array called disk, which stores the candidate distance from S to each point. And the first step is to build a grid implicitly. And the side length of each cell is R/2. We define a patch is a square area consisting of 5 times 5, which is 25 cells. And we define the cell of P is a cell that contains point P. And we define the patch of P is a patch whose central cell is cell of P, which is the big blue square in this example. And we define the unit disk of P is a unit disk centered at the point of P. And all neighboring points of P in the unit disk graph with respect to parameter R will lie in the gray region bounded by this big blue square in this figure. The basic idea is to pick a point Z with the minimum dist value in each iteration, and the dist values of points in the patch of Z will be updated. Before I enter the WX algorithm, let me introduce an important subroutine called update. So for two sets, U and V, the update subroutine will update the dist values for vertices in set V by using the dist values of vertices in set U. So in this example, for each red point V, we need to find the blue point QV from all these blue points lying in the unit disk centered at point V, such that this formula, dist U plus the distance between U and V, is minimized. Okay, so and then the dist value of V will be updated to the minimum one of these two values, original one and the dist value of QV plus the distance between QV and V. And this is a framework of the WX algorithm. So we first perform some initializations and make a copy Q of P. And then we enter a while loop. While set Q is not empty, we first pick a point Z with the minimum dist value from set Q. And then we have two update subroutines. We first update the dist values of points in the cell of Z, which is the small red square, by using the dist values of points lying in the patch of Z, which points in this big blue square. And then we go back. We update the points. We update the dist value of points in this big blue square by using the dist values of points lying in the small red square. And then finally, we remove points of in this small red square. We remove these points from set Q until we perform all of these operations until set Q is empty. And then the dist values are the shortest at the lengths of the shortest passes from point S to all other points. In the first update, we need to find a point QV in this red circle for each red point V in this small red square, such that this formula is minimized. If we assign a weight of dist U to each point, to each blue point in this big blue square, which is the patch of Z, then we have a key observation that the weighted nearest neighbor of each red point in this big blue square must lie in this red circle. So we can finish the first update by building an additively weighted Venn diagram on vertices in this big blue square. This can be done in n-log n time. And in the second update, the key observation doesn't hold. But we have another observation that this big red square had a constant number of cells. So we can perform the update subroutine for each cell in this big red square. And so we have two cases. In the first case, the cell being updated is also the cell containing point Z. Since the distance between any 2 points in each cell is at most R, so this case can be done by building an additively weighted Venn diagram on vertices in this small blue cell. And the second case is a little bit difficult, but we have that the cell being updated, and the cell containing point Z are separated by an axis parallel line. So we can perform the second update by this procedure. The first step is sorting all the points of U, which is these blue points, by the distant values in an increasing order. And then the second step is to compute a group of subsets from set U, which is these red points. So for each red point V, we need to find the smallest index IV, such that V is within the unit disk centered at point UIV. And then V is assigned to the subset of V with the index IV. This can be done in k log k time, where k is the total number of points inside U and V. So we get an example. In this example, V1 and V2 are within the unit disk centered at U1. So V1 and V2 are in the subset of V1. And V2, V3, and V4 are within the unit disk centered at point U2. But V2 is already in the subset capital V1. So capital V2 only contains points V3 and V4. Similarly, we have the capital V3 contains points V5. Then, this part can be viewed as another problem called offline insertion only additively weighted nearest neighbor problem. We will be given a sequence of insertions, which are these blue points, and we need to answer a group of queries, which is to query the weighted nearest neighbor for each red point from these blue points. This can be done in k log square k time. Next is our parametric search. So the first step is to building the grid. We need to shrink the interval R1, R2 to R1 prime, R2 prime, such that if R star doesn't equal R2 prime, then the grid with respect to parameter R, where R is in the shrunk interval, has the same combinatorial structure as the grid with respect to parameter R star. So this can be done in n-log cubic n time by using the sorted matrix searching technique with our decision algorithm. And then we consider the rest of the WX algorithm. We notice that only one step of the second update needs to be parameterized, which is computing a group of subsets of V. So the target, we first let IV of R denote the index of the subset of V that contains point V when the WX algorithm runs on parameter R. Then the target of this step is to shrink the interval such that if R star doesn't equal R2 prime, then for any red point V and any parameter R in the shrunk interval, IV of R equals IV of R star. And other steps are independent of parameter R, so we can just proceed and follow the original WX algorithm. Next is our divide and conquer procedure to solve the parametric search of computing a group of subsets of V. We have an observation that for any blue point V in the capital V, if the unit disk centered point Uj contains V, then IV of R is less than or equal to J, while Uj are already sorted by the increasing distant values. And then we partition the set U. Let U1 be the set of the first half points of U. And then in this example, it's U1, U2, and U3. And then we compute the upper envelope of disk centered at the point of U1 with radius of R above line L, which is the red curve in this example. And then we shrink the interval R1, R2 to R1 prime, R2 prime, such that if R star doesn't equal R2 prime, then for any point V and any parameter R in the shrunk interval, V is below this upper envelope, if and only if V is below the upper envelope with respect to parameter R, if and only if V is below this upper envelope with respect to parameter R star. This can be done in n log cubic n time by a procedure in a previous work proposed by Wang and Zhao in 2021. And then let V1 denote the set of points in V that are below this upper envelope. This example is V4 and V7. And then for any point V in V1, the IV of R is equal to IV of R star and is less than or equal to the cardinality of U divided by 2. And for any point V that is not in V1, IV of R is equal to IV of R star and is larger than the cardinality of U divided by 2. So we can recursively solve the next two instances. The first one is defined for U1 and V1, and the second one is defined for the rest of the red point and blue points. Until the base case is given, which the number of red points is only is 1, and the base case can be easily solved. One level of recursion can be done in a total of n log cubic n time, so all the levels of the recursion can be done in n log to the first n time. And suppose the destination point T is within a cell of Z in an iteration, then R star is equal to R2 after this iteration. This can be done so the destination point T can be reached in order of n iterations, and this could cause a running time of n squared. So we need to improve this result. The first step is building a grid as before, but next we need to classify the cells of the grid as two types, the large cell and the small cell. The threshold n to the 3 over 4 times log to the 3 over 2n is carefully chosen to balance the running time. And next we pre-process all small cells, restrict the interval such that if R star isn't equal to R2 prime, then for any 2 points UV lying in a pair of neighboring small cells, an edge connects U and V in unity graph with respect to parameter R. R is in the shrunken interval if and only if an edge connects U and V in the unity graph with respect to the best parameter R star. So since each small cell contains at most this number of points, so the preprocessing can be done by using a subroutine of the distance selection algorithm proposed by Katz and Sharia in 1997 with our decision algorithm in n to the 5 over 4 times log to the 5 over 2 n time. And then we enter the main loop. We need the main loop of parameterizing the WX algorithm. For each pair of cells in second update of an iteration, if both involved cells are small cells, we know the connections between points in neighboring small cells after the preprocessing of the small cells, so we can just run the original WX algorithm. So the total running time for this case is n log square n. And if at least one involved cell is a large cell, we just apply the parametric search. The number of large cells is at most n to the 1 over 4 over log to the 3 over 2 log to the 3 over 2n, and each pair can be solved in n times log to the fourth n time. So this case costs a total of n to the 5 over 4 times log to the 5 over 2n time. This is the same as the running time of our preprocessing for all small cells. So the total running time for our L2 weighted case, for our L2 weighted RSP algorithm is also n to the 5 over 4 times log 5 over 2 n time. Okay, thank you very much.